think for a second about something really, really intricate.
Okay.
Like how millions of cars move through a city. Or maybe a power grid, how it gets energy where it needs to go, just when it's needed.
Yeah, these huge systems.
Yeah.
So many interacting parts.
Exactly. And somehow they often seem to sort of muddle through, adapting and, well, kind of optimizing themselves.
Mhm.
How does that even happen? That's the big question, right? How complex systems learn how they get better. And that's what we're tackling today.
Precisely. We're doing a deep dive into reinforcement learning RL, but with a specific angle,
Which is?
how it works in what we're calling dynamic and socialistic environments.
Okay, dynamic and socialistic. Break that down.
Think scenarios that are, constantly changing, in flux, and also involving lots of decision makers, agents, all influencing each other.
Right. Not just one thing learning in isolation.
Exactly. And we've got this source material. We're just calling it pasted text, which kind of walks us through it.
Curated guide.
Yeah, a shortcut, really, to understanding some pretty powerful machine learning concepts.
So think of this pasted text as your, cheat sheet for getting how these intelligent agents...
And agents can be software, robots,
Yeah.
anything making decisions.
Right. How they learn just by, interacting with their world.
They try things out, take actions.
Give feedback.
Rewards or penalties.
Mm.
And they adjust, constantly adapting their approach.
It's a loop then. Learning, adapting, learning.
A continuous loop, yeah.
Okay, so let's get into it. To start us off, what are the absolute, core pieces, the building blocks of any RL system?
Okay, yeah. Fundamentally, RL has a few key elements. First, there's the agent.
The decision maker.
Yep. And the agent operates within an environment.
Its world.
Right. The agent sees its current situation. We call that the state.
What it knows right now.
Based on that state, the agent chooses an action.
Makes a move.
And then the environment gives back a reward.
Feedback. Good move, bad move.
Basically, yeah. A signal saying if the action helped or not.
Yeah.
And over time, the agent builds up a policy.
A policy.
Which is essentially its strategy. How it decides what action to take in which state.
Its rule book.
Kind of. And finally, there's the value function.
Okay, what's that?
That helps the agent predict the total future reward it expects to get, starting from a particular state. It's looking ahead.
Got it. So agent, environment, state, action, reward. Those seem pretty clear. Policy is the strategy. Value function is predicting the future score.
Yeah, that's a good way to put it. The policy is when I see X, I usually do Y.
Okay.
The value function is more if I'm here now, how good are my prospects overall down the line?
Makes sense. Can we make that more concrete, like an analogy?
Sure. Think of a self-driving car. That's the agent.
Right.
Navigating city traffic, that's the environment. Its current location, the cars around it, traffic lights, that's the state.
It's awareness.
Exactly. Actions are things like accelerating, braking, changing lanes.
The moves it can make.
And reaching the destination faster, or maybe more safely, that's a positive reward.
The goal.
Now, the car's overall driving strategy, maybe it prefers the right lane unless it needs to pass. That's its policy.
Its default behavior.
And the value function. That could be its estimate of, say, how long it'll take to get to different points ahead, given the current traffic.
Ah, okay. That helps. So dynamic environments, you mentioned those earlier. That's like the traffic, right? Always changing.
Exactly. Constantly in flux. Things are unpredictable.
So how does RL handle that if the rules keep changing?
Well, that's where model-free RL really shines.
Model-free?
Yeah, really dynamic situations. Trying to build a perfect fixed map or model of how everything works is, well, often impossible or just too hard.
Okay.
So model-free methods learn directly from experience. They don't need that explicit map.
They just learn as they go.
Pretty much. And Q learning, which our source mentions, is a key technique here.
Q learning. Right. What's the main idea?
Q learning focuses on figuring out the value of taking a specific action when you're in a specific state.
Okay. The value of an action in a situation.
Exactly.
Yeah.
It answers the question. If I do this right now, what's the likely long-term payoff?
How does it calculate that payoff?
It uses something called the Bellman equation. The text mentions it. You don't need the deep math, but think of it as a rule for updating its estimate.
An update rule.
Yeah. With every new experience, every action and reward, it refines its estimate of that action's value in that state.
So it learns from consequences.
Precisely. And the beauty is it can learn the best thing to do even if the situation is new or changing, just by trying things and seeing what leads to better rewards over time.
Learning by doing, but with a memory for what worked.
You got it. Now, the pasted text also brings up policy gradient methods.
Right. How are they different from Q learning?
They take a slightly more direct approach. Instead of focusing first on the value of actions,
Yeah.
they try to directly learn the optimal policy itself, the best overall strategy.
Ah, okay. Straight to the strategy.
hmm And this can be really useful when the agent has, like, a huge range of possible actions, especially continuous
It's
actions.
continuous, like not just left or right, but turn the wheel 15 degrees.
Exactly. Or think about something like negotiation over a shared resource. It's not just share or don't share. There's a whole spectrum of possibilities, right?
Makes sense. Nuance.
Policy gradients can often handle those kinds of nuanced, continuous action spaces better than methods that try to value every single discrete action.
Okay, interesting. So model-free RL is great for adapting on the fly in changing worlds.
Right, when you don't have or can't rely on a fixed model.
But what if the environment does have some predictability, some stable rules?
Well, then you might look at model-based RL.
Model-based, so these do try to build that map.
Exactly. Model-based methods actually try to learn an internal model of how the environment works. The agent tries to understand, if I do this, then that will probably happen.
It learns the physics of its world, so to speak.
Sort of, yeah. The source mentions DynaQ and Monte Carlo tree search, MCTS, as examples.
MCTS, I've heard of that with games, like Go.
Exactly. These techniques are really powerful for longer-term planning. If the environment has some structure, having a model lets the agent simulate possibilities, think ahead, and strategize more effectively.
Like in chess or Go, where the rules are fixed even if the opponent's moves aren't.
Perfect example. The model helps explore those future possibilities.
Okay, so we have single agents learning in dynamic worlds using model-free or model-based approaches, but the text really leans into these socialistic environments.
Right. Multi-agent reinforcement learning. MARL.
MARL. This is where it gets really complex, I imagine. Multiple agents all learning at the same time.
Absolutely. It adds a whole new dimension of complexity because now the environment isn't just changing on its own.
It's changing because the other agents are learning and changing their behavior too.
Precisely. That's the core challenge. The simplest approach here is something called independent Q learning, or IQL.
Independent Q learn.
Yeah, basically each agent just runs its own Q learning process. It treats the other agents as just part of the scenery, part of the dynamic environment.
So, everyone for themselves.
Pretty much. Like our self-driving cars again, each one optimizing its own route, maybe causing traffic jams for others without coordinating.
Yeah, I can see how that might not be optimal for the whole system.
Often it's not. It can lead to unstable learning or suboptimal outcomes for everyone.
So how do you get them to cooperate, to work together?
That brings us to cooperative MARL.
Cooperative. Okay.
Here, the agents are trying to achieve shared goals. They might get team rewards, based on the collective performance.
So they win or lose together?
In essence, yes. Techniques mentioned include things like joint action learners,
Joint action.
where agents try to explicitly learn the value of combined actions. What happens if I do A and you do B?
Okay. Requires more coordination.
Definitely. And another approach is centralized, critic decentralized actors, or CCDA.
CCDA. Sounds complex.
The idea is often you have individual agents, actors, making their own decisions.
Decentralized.
Right. But there's a central critic that evaluates the overall outcome, the team performance.
And gives feedback.
Exactly. It helps guide the learning of the individual actors, steering them towards actions that benefit the group.
That sounds potentially much more powerful for, say, that traffic light example.
For sure. Imagine traffic lights coordinating across a whole city using something like CCDA to optimize overall flow, not just their single intersection. The potential gain is huge.
It makes total sense. Working together for the greater good. But what if they aren't supposed to cooperate? What if they have conflicting goals?
Right, that's competitive MRL. The source touches on this too.
Competitive, like games again, or auctions.
Exactly. Situations where agents are adversaries. One agent's gain might be another's loss.
So how does RL work there?
Well, one technique mentioned is minimax Q learning.
Minimax.
Yeah, it comes from game theory. The agent tries to maximize its own reward while assuming the opponent is trying to minimize it.
So it's planning against the worst-case move from the opponent?
It's essentially, yes. It's about finding the best strategy in an adversarial setting.
Okay. Wow. So RL can handle cooperation and competition between multiple agents.
It provides frameworks for both, yeah. The though the challenges are significant in both cases.
Let's talk applications. We mentioned traffic lights, energy grids. Where else, based on the source, could these MRL techniques, especially in these shared socialistic systems, really make a difference?
Well, the pasted text gives some great examples. Traffic signal control, as we've discussed, moving beyond simple timers to truly adaptive coordinated flow.
Right.
Energy grids are a huge one. Imagine decentralized agents managing local solar panels, batteries, and usage to balance the grid more efficiently and resiliently than just central control.
Especially with renewables being intermittent.
Exactly. RL can help manage that variability. Healthcare resource allocation is another fascinating area.
How so?
Dynamically assigning beds, staff, or equipment based on real-time patient needs and resource availability across maybe multiple hospitals.
Adapting to surges and lulls.
And even managing public goods. Things like optimizing water distribution in a drought or coordinating efforts to manage air quality across a region.
Trying to ensure fairness and efficiency.
That's often the goal, yes.
So, across all these different applications, what are the main sort of optimization objectives? What are people trying to achieve with RL in these systems?
It boils down to a few key things. Number one is usually maximizing rewards.
Getting the best outcome.
Yeah, whether that's for one agent or ideally for the whole system, the collective benefit.
Okay.
Second is often fairness or social welfare. How are those benefits distributed? Is it equitable?
Right. Not just efficient, but also fair.
A big one is adaptability.
Yeah.
The system has to be able to cope with constant change, learn and adjust on the fly.
Because the real world is messy.
Absolutely.
Oh.
And finally, scalability. The solutions need to work not just with two agents, but potentially with thousands or millions.
That sounds like a massive challenge in itself.
It is.
Which leads nicely into the challenges. It sounds amazing, but implementing this must be hard. The text mentions some hurdles.
Oh, definitely. It's not easy. A huge one is non-stationarity.
Non-stationary.
Remember how other agents are also learning?
Yeah, changing their strategies.
So from any one agent's point of view, the rules of the environment are constantly shifting because the other players are changing. It's like trying to hit a moving target that's also learning to dodge.
Makes learning a stable strategy really difficult.
Very. Then there's partial observability.
Meaning agents don't see everything.
Exactly. An agent usually only has local information. It doesn't know the full state of the entire system.
Right.
Like driving in fog, you only see a little bit around you.
Makes optimal decision-making tough.
Definitely. And in cooperative settings, you have the credit assignment problem.
Credit assignment.
If the team does something good and gets a reward, how do you know which agent's specific actions actually caused that success?
Who gets the credit or the blame?
Right. It's hard to figure out, especially when many actions happen before a reward arrives.
Tricky.
And finally, just basic communication. How do agents share information effectively? Too much communication can overload things. Too little means they can't coordinate well. Finding that balance is key.
Okay, so non-stationarity, partial observability, credit assignment, communication. Quite a list. It's clearly not just plug and play.
Not at all. These are active areas of research.
But even with those challenges, as our deep dive into this pasted text shows, reinforcement learning offers this, well, incredibly powerful set of tools.
It really does. A framework for tackling these super complex optimization problems in systems that are dynamic and involve many interacting parts.
The key takeaway seems to be that RL lets agents learn how to behave optimally just through interaction.
Exactly. Even when the world is constantly changing around them, even when they're interacting with other learners. It's a different way to build intelligent, adaptive systems compared to traditional programming.
Which brings up a final thought. Thinking about these big challenges, RL faces the non-stationarity, the partial observability.
Yeah.
Doesn't that sound a lot like, well, us? We operate in our own complex social systems, economic systems, where we rarely have the full picture, and everyone else is also constantly learning and adapting.
Huh. That's a really interesting point.
So maybe the principles behind RL, how it tries to navigate that uncertainty and learn through interaction, perhaps there are lessons there, not just for building AI, but for how we might think about navigating our own complex, ever-changing world.
Beyond the algorithms, lessons in adaptation and learning under uncertainty.
Yeah.
It's definitely something to mull over.